think of only making what already exists. So let's take, for example, plastic water bottles that we're used to. Most of that is made from something called polyethylene. And so if I say I want to make a biomass-derived ethylene, then that already restricts the way I can use that material because I know the properties of ethylene. Instead, we can actually think about the problem from the opposite perspective. So we can say, what kind of properties are we interested in? If we want something, for example, that is more water absorbing, then we can try to understand what are the properties of a structure, of a material that gives us that functionality, and then think about whether or not we can access those structures from sugars. In this case, glucose is mostly what we use. And now we've turned the problem on its head. So rather than saying, here are the materials that we have, what can we make? We actually ask the opposite question of, what do we need from function, and can we encode that in the kinds of materials that we produce? So rather than just focusing on producing what we'll call direct replacements, we really look for functional replacements. That is, we try to understand what can we produce that's going to give us the end utility as opposed to being focused on a specific chemical structure. The primary challenge that everyone faces is one of economics, and that is, how do you actually get your process to be competitive with what the existing process is, in many cases processes that start from very cheaply available fossil resources. So that's something that we call a yield problem, in the sense that if we have a certain amount of starting material, we want to be able to convert as much of that material into the final product as possible, because we have some costs associated with paying for that starting substrate, and that's going to have a very large influence on the overall economics of the process. We really want our processes to be as efficient as possible. So we've started to look at ways to specifically engineer the cells to regulate how the sugar is used. And you can think of it in this way. Normally, what the cells want to do is to eat the sugar. Their objective is to take this carbon input and to convert it to more of itself. So the cells want to grow and divide. Our objective is to have that glucose be taken up, and then we want the cells to not eat it and to shift that off into product of our choosing. But the cells don't have any reason or motivation for making the product that we want. So we've been developing what we call devices, if we want to adopt a term from electronics, but these are really biological devices that allow us to tell the cells, okay, why don't you start by eating the sugar, and now you've eaten enough. And we can actually have manipulations to the system that changes the regulation and says, now you can't eat the sugar anymore. The only thing you can do is to convert it into a product that you're interested in. And just to give you an example, in some recent data that we have, in doing that, we've been able to improve the yield. And the yield, again, is how much of the substrate that goes in gets converted to the product that comes out. We've been able to change that number from 1% to over 80%, just by being able to control whether or not the cells can do what they normally want to do, which is to increase or to eat that substrate for its own purposes. So within biological engineering or biochemical engineering, and I'm in the chemical engineering department, there are a couple of different ways that we can look at a problem. We can have a very pathway or compound specific focus where we say, we're only interested in making this molecule. But we're really more interested in the broader rules, if you will, or what are the broader methods and techniques that we might want to use to be able to control how cells are engineered. And our hope is to be able to develop platform technologies that can be applied to any pathway. So for one specific compound, yes, we're interested in engineering that cell to make as much of that product as possible. But in doing so, we actually try to identify basic principles that allow us to apply those methods to other products and to other cells as well. And so that may, for us, involve not just a large amount of experimentation in a wet lab, but in some cases it can mean writing mathematical models that can help us to describe and understand the system and to be predictive about how we could then use that same approach in something later. And that way we can think about not just making specific molecules, but having an entire development pipeline that helps us to think about the most efficient ways to engineer the microbes for our specific purposes.